Alright, it is the 24th of May, 9:39 a.m. And we're going to be starting with the Hellenic foundations, building upon what we were discussing earlier with the traces of civilization, Egypt and ancient Mesopotamia. So let's get a bit of a geographical look at the historic beast we're going to be dealing with today by carving out, that space which defines what would become known as Hellenic. So this is kind of what we're dealing with. It's Greece and this little part right here which connects it to Anatolia, which is the space that is modern day Turkey. So just keep in mind we're going to be operating along along a bunch of coastal cities here. What exactly is going to be covered is the civilizations which grew out of this region next to the Aegean Sea. Let me check the camera real quick, see if it's rolling, and we're good. That looks fine. Okay, so getting into the real meat of it here, we're going to be dealing with the time period from 600 to 300 BCE, primarily focusing on Ionia, Athens, Croton, Tarentum, and we're going to be examining what exactly was spoken about mathematics from the mouths of philosophers, geometers, astronomer, mystics, and rationalists. With that in mind, I have to welcome you to what Boyer calls the heroic age, when Greeks, newly awakened to abstraction, asked not just how many, but why exactly mathematical structures worked, and at the same time, how exactly this matched with their own ideas of metaphysics, their religious ideas and whatnot. So gone are the ropes and trade ledgers of Egypt and Babylon. Here begins a new kind of math, born in argument, tempered in paradox, and driven by the desire to know. So let's start off with an example of something that the Greeks were looking at here, and that's the golden ratio. So how do you divide a line in the most balanced way possible? You can already see the sort of religious language in the way that this question is asked, insofar as it's connected to harmony. How do you divide a line in the most balanced way possible? So the Greeks weren't looking for halves, they were looking for this idea of harmony. They discovered a special way to divide a line such that the long part, short part over the short part is equal to the whole over the long part. And it's a sort of self-replicating division that became known as the golden section, the golden ratio. So this would come out to be equal to roughly 1.618, and this thing pops up everywhere, and it's behind a lot of conspiracy theories and a whole bunch of weird stuff, but it's just this ratio, insofar as we're concerned. Now, saying just that or just this is implicatively reductionistic, but not going to be discussing any sort of magical things today other than the mathematics which the Greeks found along the way. So here's some examples of, here's some figures that they found this, that they saw this a lot easier than perhaps you and I would if we were left with their material wealth and whatnot. So I'm kind of botching it here, but I'm just going to try to make up for my lack of art with speech. So, yes, okay, and yes, this connects here. That kind of looks a bit devilish, but it wasn't really a thing back then. So we see it here with this pentagram right here, all the different segments. See it here with this line, dividing this line into several different pieces, and with this figure here. And these are nothing new, nothing particularly special. There's just figures from the book which we have as demonstrating what the Greeks had in mind, what they were looking at whenever they were searching for this all too perfect golden ratio. Yeah, so this one here is a pentagram where intersecting diagonals naturally divide one another in the golden ratio. This one right here demonstrates the recursive structure of the ratio. Each subdivision replicates the same proportion infinitely. Now, another interesting thing is this one here. This one shows how to construct this division using a square and a circle alone. You can sort of see how that entails with this angle right here. Now, another one, it's just mentioning another pentagram-like shape by which the golden ratio emerges from segments. So the Greeks, especially the Pythagoreans, saw this ratio not as a number, but as a cosmic symbol, a visual echo of balance. Sort of again seeing that bend of religious language in mathematics, which would be certainly out of place today, is right well in line with Greek, I suppose you could say, theological thinking of their day. So, let's look at another such instance of this. Can you measure the area of a crescent shape? So, it should be prefaced that the circle was this sacred but unmeasurable thing. This, the idea that there's a whole infinite edge that you're dealing with. But then comes around this guy by the name of Hippocrates of Ch2. One of the things that will be demonstrated here is how separating these different points actually leads to this thing being measurable. Quite measurable, not infinite, but still, nevertheless sacred in the eyes of the Greeks. trace this up here. So this one here shows a crescent, or a lune, bounded by a semicircle, and a triangle. Now, Hippocrates proved the area of the lune equals the area of the triangle itself. A practical breakthrough really a curved figure made measurable. Now, this figure right here, it extends this idea to other configurations. And let me just show you another such configuration. This one's interesting. Yes. So this one's two lunes together equal to the area of a right triangle. But, you know, with every single development ever made, there's always going to be a few rough patches. And one such rough patch is this figure right here. So this is a failure of trying to patch together many lunes to square the full circle. Now, these early steps laid the groundwork for later concepts of integration and analysis long before calculus. The Greeks were trying to measure what bends, but as you can see, the problem is getting precise enough with the equipment that they had at the time, which was mainly just sticks and stones and, you know, lines in the sand. But not to say that they couldn't have, but it's very difficult. We'll get to squaring the full circle later. Now, here's another such problem that they dealt with, or rather wrestled with. Can the diagonal of a square be measured exactly? So the Pythagoreans believed all lengths could be expressed as ratios of whole numbers. But then came this tricky business of the diagonal of the square. So put as many lines there, and eventually one of them will be right. A, C, B, D, Q, P, R, S. Oh, whoopsies. There we go. So, geometrically speaking, this shows a recursive proof by contradiction. Assuming the diagonal is rational leads to an infinite descent. This proved that the square root of 2 is rational, or as the Greeks called it, incommensurable, with the unit length. So, you know, if this is a unit square, each of these would be 1, and if you're using the tools that we discussed earlier, you'd find that this diagonal here would have a length of square root of 2. It's rational, it's incommensurable. The discovery shattered the belief that all is number, or what the Greeks saw as number, back in the day, and forced Greek thinkers to distinguish between discrete and continuous number versus magnitude. Now, let's get on to something which they were able to wrestle with a bit more easily than a lot of our day, and that is geometric algebra, in which they sought to answer the question, can you do algebra using only geometry? So let's look at one such example in which they succeeded. Take this square, break it up into these partitions. This is one of the more famous examples. And what's interesting is this is actually a plus b squared as a large square composed of 4 parts. A squared here on the top left, b squared bottom right, and 2 AB rectangles. And you can sort of see the more inherent beauty in breaking things down geometrically as opposed to, I guess, a sort of symbolic reductionism that doesn't really capture the beauty of the geometrical and why that would have been sought after by the more aesthetically motivated, let's say, Greeks. Now, let's just continue with this and look at a different equation, a different means of looking at the world geometrically. Right, let's see if I can do this. All right. This whole length over here is A. This whole length over here is A plus B. This whole length over here is A minus B. Now, what can be garnered from that? Well, it's roughly equivalent. Well, no, it is equivalent to A squared minus B squared, or A plus B multiplied by A minus B, by rearranging a large square minus a smaller square into a rectangle. Clever. Let's take a look at another one. Oh boy, another semicircle. This one right here. Dot, 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 dot. O, and this one is B. So they used a semicircle and a right triangle to geometrically construct another one of those, well, perhaps another incommensurable. The square root of A times B. So this wasn't a workaround, it was just a robust form of reasoning in which their algebra was spatial and not just symbolic. One of the things that I remember back whenever I was in middle school was you learn both ways, but whenever it comes to the algebraic pedagogy, a lot of the internal geometrical leanings are abandoned. Not so was the thinking of the ancient Greeks. Now moving right along. How do you double the volume of a cube using only geometry? Now, why would somebody ask such a question, right? Yeah. Seems kind of crazy. Why would anybody be asking how to double the volume of a cube using only geometry? Well, if they're the only tools you have, And you get this specific instance where the Delian oracle asks the Athenians to double a cubical altar. Well, you might just wander along these strange paths. They thought they could just... Oh, and by the way, this has a lot of history behind it. The Peloponnesian War between the Athenians and the Spartans. There was a plague. The Athenians wanted a way around it, and so they talked to an oracle, and the oracle told them, hey, if you do this, then you'll be okay. But they didn't know how to do that. They thought they could just double the edge length, but that would octuple the volume. So the real challenge then was to find x such that x cubed is equal to 2a cubed. Straight edge and compass don't exactly solve it. So a Greek by the name of Metamachus, a student of Plato's Academy, invented a new tool called Conic Sections. So I'm going to attempt to draw that. Let's hope I'm successful. Not just the conic section, but all that it entails. An artist I was not made to be. Okay, let's hope that's... Just pretend that this is inside of the... There we go. Then... F-E-O-O-P Q. It's not really all that valuable, I'm just trying to get it accurate to the way the book depicts it. I mean my accuracy, not the book's accuracy. So this shows the generation of a parabola from slicing a cone. You can sort of see it here if I didn't watch the drawing too much. So you can sort of see, you can kind of pick up what they're putting down. Let me just, okay, y squared is equal to 2ax, x squared is equal to ay. Now this shows the breakthrough intersecting a parabola, and hyperbola produces a point that helps to solve this problem. And this wasn't these collisions. This wasn't just a clever fix. It marked the invention of a new kind of curve, one that would later underpin analytic geometry and the idea of coordinates, which was baffling. They didn't have a coordinate system at the time. The use of Cartesian coordinates didn't come until René Descartes, which of course doesn't come until roughly about maybe around 1,000 or so years after they had been thinking in these terms, the ancient Greeks were. So it's remarkable that they were ever able to come up with such an idea. And so, well, what do we make of this? What do we make of what we found the Greeks to appreciate from the mathematical, and how do they exactly contribute to mathematical history? Well, the core principles of proof, harmony, ontology, proportion. This was a civilization of reason insofar as we could get one, right? Not just about what works that we saw in hunter-gatherer societies, not just the tax equations of the ancient Egyptians, or how to divide up land, or anything like that we saw with the ancient Mesopotamians either. It's just that they didn't just solve problems. They defined what it meant for a problem to be solved. So imagine this, you're a student of Plato. You must prove a truth of geometry with no ruler, no calculator, and no tolerance for contradiction. What would you choose to prove this, and how would you even begin? These are the sort of things that the ancient Greeks wrestled with, this Platonic idea of something being perfect, a form, order, harmony, balance. So with that, let's turn to the greatest perhaps the greatest mathematical mind of this time. And it's debatable, but he's the one that we have on paper the most, and that is Euclid. Existing around 300 BC at Alexandria. So Alexander has obviously come around and does his thing of taking over the Persians, breaking them apart into a bunch of little tiny pieces, and naming a whole bunch of cities after himself and his horse. And we have in the echoes of that, not just a Hellenic society, not just a society defined by the Greeks, but a Hellenistic society in which these ideas from the East are transferred west from all of Alexander's conquered territories, from the almost the edge of India all the way back to around what would be considered Bulgaria, North Macedon, the Balkans area. So we're going to be dealing with these ideas from philosophers, scholars, geometers, and Platonic inheritors. So here in the bright halls of the Alexandrian Museum, geometry is no longer a craft, it is the mind's cathedral. Euclid stands at the intersection of Plato and Aristotle, compiling not just the truths of geometry, but the logic by which truth itself may be pursued. No longer will we rely on ritual or intuition. Here at last, there is no royal road. Instead, it's a bunch of wealthy people who have nothing better to do than no, but it's this beautiful pursuit of the mathematical by a handful of people who aren't exactly titled in the well, we'll get into more of that as we progress. For now, let's look into the mind of Euclid, starting with this question. How can you divide a shape with total fairness? Now, it's like this whimsical, poetic idea applied to something which is supposed to be just cold, barren calculation. And then you have this idea of fairness. It's like, what does that mean? It's kind of a fantasy insofar as geopolitical concerns are have been seen throughout the era. And yet you have this idea in this harsh world, this cruel world, by the way, which ancient Greece in reality was, despite its own rationalism, plagues going on, wiping out most of your people, all of your soldiers are dying, and Rome, which would come along quite soon, would end up losing 25% of its adult male population in a single battle. And in this cruel, unforgiving, relentless world, you dare to ask, how can you divide a shape with total fairness? Like, it's just, it's amazing. It's amazing. So let's dive into that. You're given a trapezoid. Not just any shape, but a trapezoid. One bounded by points A, B, Q, and D. The upper side, AB, is shorter than the base QD, and both sides extend upward to meet a point E, forming triangle AED. Your task is to draw a line parallel to the base that cuts the trapezoid ABQD exactly in half, dividing its area into two equal parts. This isn't guesswork, it's geometric reasoning. Let me check the camera real quick. Yeah, the camera looks fine. Okay. So, again, you want to draw a line parallel to the bases that cuts the trapezoid ABQD exactly in half. Dividing its area into two equal parts. This is our task. And now let's represent it a bit more visually. Starting off drawing the triangle already, because why not? At this point, nothing's a spoiler that we're really covering here. It's all thousands of years old. So, this is the setup. What's our punchline? Well, a line ZI is drawn from point Z on segment AE to point I on segment ED, parallel to both bases. The key insight here is that a line parallel to the bases creates a similar trapezoid, but only one such line, placed precisely, will divide the total area evenly. Now, here's a clever thing that the Greeks did in order to find this. So the Greeks used this condition. They used this condition that ZE squared is equal to 1/2 EB squared plus EA squared, where ZE is the distance from point Z to the apex E. EA and EB, those are the distances from E to the ends of the upper base. The equation ensures the area of the triangle EZI equals half the area of trapezoid ABQD. This geometric condition isn't derived from modern calculus. It's built from Euclidean reasoning and proportional logic. So this shows us that area can be reasoned about geometrically, not just measured. Visual symmetry often hides numerical balance. Construction problems in Greek mathematics reflect deeper ideas of fairness and precision. This problem comes from Euclid's lost work, Division of Figures, and represents one of the earliest known examples of geometric area bisection based on squared lengths. Let's get into another such problem. What if a figure contains its own solution? Some diagrams don't need numbers to speak. They contain relationships within them, areas that constrain each other's shapes, whose positions imply conclusions. One such shape, just this simple rectangle. It's a rectangle divided by a vertical line segment, here BF, forming two parts. If the area of one part is known, the shape itself contains enough logic to deduce the other. This type of problem is drawn from Euclid's data, which focused on what follows from what. Not through equations, but just through simple spatial reasoning. Let's go on to another problem. That is, can you build a perfect triangle, with no measurements? Imagine you're given only a segment, no ruler, no numbers. Now, can you construct an equilateral triangle? Well, yes. And here's how they did it. So, you have these line segments here. You're given only one of these. Let's just take this one. Oh, sorry. Not that, that's a little too simple. Let's do A, B, right? There we go. Okay. He draws two circles, one centered at each endpoint of the segment. And their intersection becomes the third vertex of the triangle. Each side is defined by construction, not by measurement. And this comes to be the foundation of Euclid's elements, building truth from definitions and postulates. I'm just going to go ahead and speed run it here. I'm going to show the end result, so that way I don't have to talk and do it at the same time. Oof, okay. And there we go. That one's G, this is F, A, B, H, and E. Now, this one here. G, H. There we go. Pretend that's a circle. That's going to be difficult. But he draws two circles, one centered at each endpoint of the segment, and their intersection becomes the third vertex of the triangle. Each side is defined by construction, not by measurement, as I mentioned earlier. And so we have here the perfect triangle without really turning to any sort of measurements, without specifically saying we want this side to be 3, we want this side to be 3, we want this side to be 3. You're just taking it from that one line segment and you're drawing circles, and all of a sudden there you go, a perfect triangle. Now let's go and look at another question, and that is, how do you prove a Pythagorean theorem without algebra? Well, I just show this part first, and then discuss it. Oh, okay, that's gotta be a square. That's gotta be a square. That's not good enough. There we go. So this figure, as you'll notice, contains no numbers, only squares drawn on the sides of a right triangle. It's one of the most elegant visual proofs in all of mathematics, and the reason is this: the two squares are dissected and rearranged. The pieces fit exactly into the larger square. So from this, you deduce that the area on side A plus the area on side B is equal to the area on hypotenuse C. This is Euclid's proposition 1.47. It shows that geometry can establish certainty, not just approximate results. which is quite a statement from a civilization where we're still using spheres and shields. Now let's look at another question. How do you show that multiplication distributes without multiplying anything? Scandal. We kind of saw this earlier, but let's get Euclid on it. So you have a rectangle. You divide one side into two parts. Call them B and C. And you draw lines to form two inner rectangles inside the whole. And this is the layout that we're working with right here. Now visually, becomes then obvious that A times B plus C is equal to AB plus AC. Now, this is algebra insofar as the Greeks are concerned. It's done with area. We discussed this earlier with one of the examples, but the logic of multiplication and distribution, it was grounded in shape, not symbols. Greeks probably had fairly high, what's the IQ for spatial reasoning, I think it is. Anyhow, let's ask another question. How can a square reveal a deeper and more generalized identity? And identity theft is not a joke, but this should be fun. Wow, let's take a look. Another rectangle, quite a few of those. Let's see if I can draw things properly this time. So you start with a large square, you remove a smaller one from its corner. What remains? Well, the leftover region can be rearranged into a rectangle whose sides are a plus b and a minus b. Now from this, the Greeks then saw that a squared minus b squared is equal to a plus b times a minus b. And this wasn't derived through a series of complex equations that lead to this. It was just seen. Geometry made abstract relationships visible. Here's another such example of that intuition. whenever we ask ourselves, what shape repeats itself forever and always feels balanced? And this leads us to some beautiful patterns. Start with something simple here, and then it'll get increasingly complex. But not really increasingly complex, it's just more of the same over and over again. Yes. Alright, oh shoot, wrong one. And there we go. It's roughly mid point. Okay, there. Okay. Not even drawing all of these correctly now. Okay. H. So you remove the square from a golden rectangle. What remains is another golden rectangle. And you can keep doing this. Actually, let's take a good look at that and then make more space. So I'm not exactly sure how the camera is aligning with my movements, and I won't know on this board until I look at it later. Which I should have done earlier, but didn't have the time. Okay. This reminds me of one of those scenes in spy movies where they're like, zoom in and enhance, and you can't actually do that in real life. Okay. So beta. There, H. Okay, this should be here. Should be here. Oh boy. Okay. Q R O C. Oops. Let's go ahead and make the spiral. Oh boy, okay. Okay. It's good enough. Okay, so this completes that thought that we were working on earlier. That rectangle that I had drawn right here, golden rectangle right there. Each golden rectangle spirals into the next. Hence you can see the spiral here, forming a shape that converges toward a point but never quite lands. And you kind of get that feeling whenever you're reading Plato, whenever you're reading from the Greeks of this time. It's this push towards perfection, and it just being just so out of grasp. This is an ancient glimpse into the modern concept of a limit. The Greeks called such shapes nomons, pieces that preserve the whole. Preserve the whole thing. You see this sort of, gnome, like a gnome. Also, there's this idea in Gnosticism, gnosis, a secret which you hold that leans you towards the transcendent, which all of the other plebs don't have. At least that was the idea. So too, do you have this idea of nomons, pieces that preserve the whole thing. Because, you take it, spiral, and keep going, and you can do that infinitely. Well, you can't do that infinitely because you're going to die someday. That's just the way, it's just the way all of it is. That got dark. But let's take a look at what this means, broadly speaking. So we get these, so Euclid's postulates are analogous to what we see nowadays as axioms. And we saw geometric proofs of these fundamentally algebraic ideas that we look at nowadays. The construction of that, and looking at continuity, and just the exhaustion of all the different ways we can think about things geometrically. This was a civilization of structure built to counter the forces of entropy, whether it be plague or war or famine. And so it should come as no surprise that you get these first principles, these things by which you can stand, these pillars. So they didn't just do geometry in that sense. They built the scaffolding of knowledge itself, and geometry just so happened to be that pattern by which they worked. And so with that, we'll close off the lecture for Hellenic Foundations and move on to ever-growing complexities in the history of mathematics. All right.